The word bank appears in two sentences. I deposited money at the bank and I sat by the river bank. Same spelling, completely different meanings. And somehow, modern AI systems never confuse them. They don't use dictionaries. They don't parse grammar rules. Instead, they do something far stranger. They place every word in a 768-dimensional mathematical space where meaning itself has coordinates. And here's the wild part. In this space, you can do arithmetic with concepts. King minus man plus woman actually lands you near queen. Today, you'll understand exactly how this works and why it's the foundation of every AI system you've ever used. Computers are fundamentally number crunchers. They can multiply matrices, calculate gradients, optimize loss functions. But they cannot directly process the letter A or the word elephant. So every AI system faces the same starting problem. How do we convert human language into numbers without losing meaning? The naive approach, assigning arbitrary IDs like cat equals 1, dog equals 2, fails immediately because it implies dog is somehow more than cat, or that the difference of 1 means something. We need a representation where mathematical relationships reflect semantic relationships. The first serious attempt was one hot encoding. Imagine a vocabulary of 10,000 words. Each word becomes a vector of 10,000 dimensions where exactly one position is 1 and everything else is 0. Cat might be a 1 in position 4,321. Dog might be position 2,047. Simple, unambiguous, and completely useless for understanding meaning. Why? Because in this space, every word is equally distant from every other word. Cat is as far from dog as it is from quantum or democracy. The geometry tells us nothing about semantics. The breakthrough came from linguistics, not computer science. In 1957, John Firth wrote, "You shall know a word by the company it keeps." This distributional hypothesis says that words appearing in similar contexts have similar meanings. Think about it. You've probably never looked up smartphone in a dictionary, but you know exactly what it means because you've seen it used alongside apps, screen, battery, call. If two words consistently appear near the same neighbors, they probably mean related things. This insight transforms our problem. Instead of hand-coding meaning, we can learn it from patterns in text. In 2013, Tomas Mikolov at Google introduced word2vec, and everything changed. The idea is deceptively simple. Train a neural network to predict a word from its surrounding context, or predict context from a word. The network has a hidden layer with, say, 300 neurons. After training on billions of words, those 300 neurons learn to encode meaning. The weights connecting each word to this hidden layer become that word's embedding, a dense 300-dimensional vector. Words that appear in similar contexts naturally end up with similar vectors because the network learned to activate similar patterns for them. Here's where embeddings become genuinely surprising. Remember that king minus man plus woman equals queen example? It actually works. The vector for king minus the vector for man captures something like royalty without maleness. Add the vector for woman and you land remarkably close to queen. This isn't programmed. It emerges from the training process. Similarly, Paris minus France plus Italy lands near Rome. The embedding space has learned to encode relationships as directions. Gender is a direction. Capital city of is a direction. Tense is a direction. Meaning has geometry. Why 300 dimensions? Why not 3 or 30 or 3000? Think of each dimension as capturing one aspect of meaning. One dimension might loosely correspond to animate versus inanimate. Another might capture concrete versus abstract. Another might encode formality. No single dimension has a clean interpretation. They're distributed and entangled. But collectively, they span a space rich enough to position millions of words meaningfully. Too few dimensions, and you can't separate concepts. Too many, and you overfit to noise or waste computation. Empirically, 100 to 300 dimensions hit the sweet spot for word embeddings. Word 2vec has a critical flaw. Remember our bank example? In word 2vec, every word gets exactly one vector. The financial bank and the river bank share the same embedding. An awkward average of all their uses. This is the polysemy problem. One word, multiple meanings, one vector. The embedding for bank ends up somewhere between money and river, which is semantically meaningless. For many applications, this averaging effect is acceptable, but for tasks requiring precise disambiguation, we needed something better. We needed context-dependent embeddings. Enter transformers and models like BERT. Instead of one fixed vector per word, these models generate a different embedding every time based on the surrounding context. The word bank in river bank gets a different vector than in bank account. How? The transformer processes the entire sentence simultaneously, using attention mechanisms to let each word look at every other word. The embedding for bank incorporates information from river or account depending on what's actually there. Context doesn't just help interpretation, it fundamentally changes the representation itself. We've talked about word embeddings, but AI often needs to understand entire sentences or documents. Early approaches simply averaged word vectors. Crude but surprisingly effective for some tasks. Modern methods like sentence BERT train specifically to produce meaningful sentence embeddings where semantically similar sentences cluster together. You can embed an entire paragraph into a single 768-dimensional vector. Two paragraphs about climate change will be nearby in this space, even if they share no exact words. This enables semantic search, finding content by meaning, not keyword matching. How do we actually measure if two embeddings are similar? We could use Euclidean distance, the straight line between points. But in high dimensions, this has problems. Vectors can have different magnitudes for reasons unrelated to meaning. A more robust choice is cosine similarity, the cosine of the angle between two vectors. If vectors point in the same direction, cosine similarity is 1. Perpendicular vectors give 0. Opposite directions give -1. This focuses purely on direction, the orientation of meaning. Ignoring magnitude. When you ask ChatGPT a question, it's using cosine similarity behind the scenes to find relevant context. Here's a practical problem. You've embedded 1,000,000 documents. A user query comes in, you embed it, and now you need to find the most similar documents. Comparing against all million using brute force cosine similarity would take forever. Vector databases like Pinecone, Weaviate, and Milvus solve this using approximate nearest neighbor algorithms. They build index structures, often using techniques like OCHNSW, hierarchical, navigable small worlds, that let you find the top similar vectors without checking every single one. Query time drops from seconds to milliseconds. This is the infrastructure behind semantic search and RAG systems. Retrieval augmented generation has become the dominant architecture for making large language models useful with private or current data. Here's the flow. Your company documents get chunked and embedded into a vector database. When a user asks a question, their query gets embedded and used to retrieve the most relevant document chunks via similarity search. These chunks are then injected into the LLM's prompt as context. The model generates an answer grounded in your actual data, not just its training knowledge. Embeddings are the glue. They're what makes find relevant information actually work. Without good embeddings, RAG falls apart. Embeddings aren't limited to text. Models like CLIP learn to embed images and text into the same vector space. A photo of a dog and the phrase a golden retriever playing fetch end up near each other because they represent similar concepts. This enables mind-bending applications. Search your photo library with text queries, generate images from descriptions, find images similar to a text concept. The same principle extends to audio with models like Whisper's embeddings, or even to code, molecules, and user behavior. Any data type that can be meaningfully compared can theoretically be embedded. 768 dimensions are impossible to visualize directly, but techniques like t-SNE and UMAP let us project high-dimensional embeddings down to 2D while preserving neighborhood structure. Points that were close in 768D stay close in 2D. The results are stunning. You'll see words or documents naturally cluster by topic, with clear regions for sports, politics, technology, cooking. These visualizations aren't just pretty, they're diagnostic tools. If you're embedding show Apple, the company mixed in with Apple the fruit cluster, you know you have a disambiguation problem. They reveal what the model has actually learned. How do you know if your embeddings are actually good? Standard benchmarks test analogy completion, word similarity correlation with human judgments, and downstream task performance. But the real test is your specific use case. If you're building a customer support search system, the question is, do queries actually retrieve helpful answers? Embedding models optimized for general language might fail on domain-specific jargon. A legal document search system might need embeddings fine-tuned on legal text. Always evaluate on data that looks like your production traffic, not just academic benchmarks. Let me save you some debugging pain. First, embedding models are sensitive to input format, casing, punctuation, white space. Machine learning might embed differently than machine learning. Second, long text gets truncated to a maximum token limit, often 512 tokens. Critical information past that limit is simply lost. Third, embeddings encode biases from training data. If the training corpus associates engineer with he, that bias lives in your vectors. Fourth, different embedding models produce incompatible vector spaces. You cannot meaningfully compare embeddings from BERT and Word2Vec. Always embed with consistent models. Embeddings continue to evolve rapidly. Sparse embeddings from models like Splade combine the interpretability of keyword matching with semantic understanding. Matryoshka embeddings let you truncate vectors to different lengths depending on your precision storage trade-off. Instruction-tuned embedding models follow specific prompts like embed this for retrieval versus embed this for classification and adjust accordingly. And as context windows grow, the line between embeddings and full model reasoning blurs. What remains constant? The fundamental insight that meaning can be geometry and geometry can be computed. Let's lock in what you've learned. First, embeddings convert words, sentences, and documents into dense numerical vectors where geometric relationships mirror semantic relationships. Similar meanings, similar positions. Second, modern contextual embeddings from transformers solve the polysemy problem by generating different vectors for the same word based on surrounding context. Third, vector databases and approximate nearest neighbor search make similarity operations practical at scale, powering RAG systems, semantic search, and recommendation engines everywhere. Next up in the AI track, we're diving into attention mechanisms, the actual machinery inside transformers that makes contextual embeddings possible. Subscribe and hit the bell so you don't miss it. Now I want to hear from you. What's one application where you'd use embeddings that we didn't cover? Drop it in the comments. I read every single one.